last lecture and the lecture before, we looked a little bit at structs. We saw some of the syntax, and we also encountered a new powerful tool in C to do dynamic memory allocation. That is, ask the operating system for memory beyond that which it was just allocating for our variables when we declared them. This was our malloc syntax. So here we have a simple struct that contains a few strings, S facts. So these are going to be our struct facts. We've got a few facts about structs before we're ready to move on. We encountered a few pros of structs. The first was that they made grouping chunks of data together that were logically related much easier. Again, thinking back to our example of a person who had a name, an age, a place of origin, and other attributes about themselves. They're also pretty flexible in that it's very easy in your code to go back to where you declared a struct and add another field to it. So if age, name, and origin weren't enough, but we also wanted to know star sign, it would be very easy to add a single line to our struct and add the star sign in. In this way, we wouldn't have to modify any of the function prototypes. We could just modify the struct, and all of our functions would stay the same throughout the code. It also allows us to return multiple items from a function, even when C normally just allows us to return a single item for a function. Because, of course, after calling a function, you can return a struct. And if you return a struct can have multiple items, and so in essence, you are returning multiple items from the function overall. It was also a pretty nifty and neat syntax for maintaining code and made things much more readable. And it allowed for data hierarchy, so you could have nested structs, structs within structs, pointers within the structs that linked back to more outer elements, just like the Russian Matryoshka dolls. Or the Eastern European Matryoshka dolls that have their cute little nesting structure as well. There were, unfortunately, some limitations of structs as well. One of these we haven't encountered yet pertains to how you compare structs with each other. Does anyone have a sense of why it might be difficult to compare two structs? Let's say we have two student structs. I can't see them here today, but Josh and Laura were our two students. If we have a struct for each of them, why might we have some difficulty comparing them directly? Okay, so why might we have difficulty comparing two structs that are, say, each a person?
Because it takes a lot of memories and time, does it?
Have a think about it. What does it mean to compare two people? You're thinking the right thing.
How could you tell?
Because I know the expression. Andy is thinking that, it's actually, what does it mean to compare two people? That doesn't make much sense. Well, if they both have an age, could we compare their ages? But is comparing the ages the same thing as comparing the people?
No.
No. So is the question I'm asking really a good question? Like, what is the result of Josh greater than Laura?
No.
No, it's a bad question, which is exactly why C doesn't allow us to compare structs directly, because we haven't told the computer or the compiler or the program what actually it means to compare structs. Structs have a lot of different fields, and comparing is one greater than the other or is one equal to the other isn't necessarily well defined unless we've already told the program what we mean by that, what kind of semantic or underlay is there, and what we mean for it in the world. So we could write, for example, a function that compares two people that just tells us who is older, but that would probably better be labeled who is older rather than compare people. And that's why C doesn't allow us to do this. So you'll see on there, up on the board, if YA is greater than XC, that's invalid, or if YA is equal to XC, if they're both students, none of those comparisons make sense. You'd have to write a special comparison function in order to make that work. And bonus points if you can guess, but don't say it out loud what YA and XC stand for. Now that we've seen a number of examples in the class of using structs, and we've also seen a number of ways of using arrays, you might think that they're wholly interchangeable. After all, both can be used to store collections of data. There are unfortunately some key differences, particularly with regards to C syntax, and traps to fall into that you've got to be careful when you're deciding how you store your data. In particular, you can't assign two arrays to be equal to each other. If you have an array A and array B, and you say A equals B, that's not going to work. Both arrays will have multiple elements, and you haven't explained to the program what it means to set one array equal to the other one. It's just a collection of different chunks of memory. However, you can do this for structs. This is a function feature that C allows. It thinks, okay, if you're going to assign equality in structs, you must mean you want all the fields of one to be equal to all the fields of the other. However, there are more traps here. What if one struct has within it an array? If your struct type has within an array, and you set struct A equal to struct B, or if you have pointers, what does that mean? I'm going to leave these questions unexplored for now, but I encourage you to go home, write a couple of experimental programs, and see what happens for yourself. Arrays and structs can both be given as arguments to functions. We saw what that meant for structs. It meant we actually copied the whole struct, which would be pretty slow. When you pass an array, however, this is treated just like a pointer, and so it was more efficient. We did have a workaround for this, though. We could take the address of a struct and pass that into the function, giving us much more flexibility and allowing us to make far fewer copies overall while still preserving the underlying idea of wanting to transfer the information around different parts of our program. We can also return both of these different elements from functions, but you'll notice, again, arrays, what we're actually doing when we return an array, we're not returning the contents of the array, we're returning a pointer to the array. Therefore, if in, say, a subroutine or a subfunction, you create the array and try and pass it back, it won't work. You've passed back a pointer to memory that no longer exists. Remember, when the function ends, all the memory that was allocated within that function, assuming it was on the stack, gets destroyed. This isn't true for malloc, which we talked about yesterday, but we'll see examples of that shortly. You can't take an address of an array. You can take an address of elements in the array, but the array itself is already a pointer. So if you do take the address, you won't get the address of the array, you'll get the address of the pointer to the first place in memory. So you'll have a pointer to a pointer, which many times is not what you're trying to do. Remember, if you want a pointer to where the array starts, that's just the name of the array by itself. With structs, you can take the address of it. The struct is just like a really big stack variable with a bunch of different fields, and so you can take the address of that and pass it around to functions and use it in the efficient way we described. You can also, as a result of this difference, use the name of the array directly as a pointer in all the places that you'd normally use a pointer. The same is not true of structs. Again, structs refer to a normal variable that's kind of like subdivided up. And so if you want to use a struct like a pointer, you have to take the address of the struct. So that should be a nice, clean recap of the difference between structs and arrays and some of the reasons why you might choose to use certain syntax with one or certain syntax for the other, or even more why you'd try and use one logically in a certain instance in your code. If you have a large collection of objects of the same type, that's probably an array. If you have groups of fields that are of different types, so like a person with age, name, origin, that's a more appropriate use for a struct. Even if you have multiple people, then you can have an array of structs, so an array of people or an array of students. This gives us a mapping, another form of abstraction to add to our list of abstractions that we already have. We have functions that are our abstraction over execution. They allow us to divide up our execution into nice, neat, nifty parcels that are, for your assignment at least, less than 50 lines in length. And so we also have an equivalent mapping for data. Data can be stored in structs, which give us these nice, tidy little packages through which to arrange the organization of our data. These are both types of abstraction. There are certainly more than what I've just put up here, but these are to add to your toolkit to help you conceptualize and how to break up both execution and information. We have a few more things to learn about malloc today before we go on to some of the really powerful use cases for malloc. And these are I'm particularly excited about. We'll see whether we get to them today. This is some example syntax or a template for how you'd use malloc. I'm going to leave this here in the slides for you to look up later and work through. But we've already seen this in its practical use case in a number of instances. The first thing is you need a pointer. Then you give memory to that pointer by telling the operating system that you want to assign it a certain amount of memory. So that's our third line over here. Pointer equals malloc how much memory we want. We have our sizeof operator that allows us to figure out how much a single element of a given type consumes in memory. We then have a check to see if malloc succeeded. If the pointer is set to an actual memory address, we know that the allocation succeeded. If it's still 0, or if it's some value other than a valid memory address, we know that there is no memory available. We have an assertion there just to make doubly sure. And then we do some stuff with the pointer. When we're done, we free the pointer, and then we set the pointer back to null to make sure that we're all aware that there's no valid memory that we have allocated to us anymore. Here is an example of a simple struct and mallocing space for that struct. This is going to be our Boeing 747, a Qantas Boeing 747, or that should be a 737 actually with that few seats. Unfortunately, none of them are flying anymore. I flew on one of the very last flights of the 747, made me very teary. Anyway, so we have our plane type and we have a seat type. I'm not showing you what the seat type here, but imagine we have a seat type that contains the passenger at every seat, whether it's a business class seat or an economy seat, whether it's a middle seat or an aisle seat, all the information that you might want to have in your struct about a seat. And we're going to need to allocate some memory for them. In this case, we need to allocate memory for 174 seats. And so we set our pointer plain seats, which is going to contain space for all the seats that we want, and we malloc it size of seat t, so the size of one seat, multiplied by the number of seats on our plane. Fairly standard syntax. Attention passengers, due to pilot availability, we are changing your gate to accommodate a larger plane. Unfortunately, a 747 is no longer available. We now have a 787 with 246 seats. This is considerably larger than our plane before, but we still want to be able to have room for all the seats. If you think about it though, we've got a bit of a challenge because we only malloced enough room for 174 seats, but we still have the same passengers. We still want all their data. We don't want to throw out all their data, but we need room for more seats and for more passengers on our plane. So we've got two questions to explore now. What can we do if the memory we malloced isn't enough for the new plane's extra seats, or you could imagine this for any type of data when we get new data and the amount that we've allocated isn't enough? And then question two, how can we transfer the information from the memory that we allocated originally to the new memory that we've got once we've got a larger spot of memory for our plane seat? Why don't you help us out approaching these two questions? So what can we do if the amount of memory we malloced before isn't enough? What are our options?
We could malloc a new array, which has enough for the extra seats.
And if we malloc a new array, what do we then do with all the old passengers' information?
We copy it over to the new array.
Can you give me a sense of how I might copy it over?
Just copy each element in one at a time.
And in C syntax, how would we do this?
We would loop through all the old seats using a for loop, and then write to the new array.
That sounds like a pretty good idea. Let's see what I said about this. Well, option 0, we could try and just use extra memory at the end of our old malloced plain seats. Would this be a good idea? Why? Yes or no?
We haven't allocated it, so we shouldn't use it. We might get a segmentation fault.
Seg fault, very good. That was the right answer. Option 1 that you outlined for us, the other option 0, no good. Option 1, manual copy. Let's see how we do this. Well, we could malloc some new memory for our new plane. Then, as Dougal suggested, we have our loop over the old plane's seats. So from I0 to the old plane seats, and for each seat, copy the data that was in the old seat into the new seat, assuming that we've written some copy seat function. And when we're done, free up the old plane seats. Seem reasonable?
Yeah.
Do you think that there might be a more efficient way of doing this?
If the memory that's immediately after the memory we allocated previously is unused, then we might be able to ask for that specific block of memory.
So let's hold that thought for a minute, but probably a good idea. So we have another option, and this is the realloc function. Thank you very much, Dougal. This is a function built into the C standard library and part of the POSIX specification. Again, this was a bunch of functions that pretty much every Unix-based operating system has. So we've got this realloc function, which is going to ease some of the difficulty here. And we'll turn back to Dougal's idea about maybe making things more efficient in a second. Maybe realloc's the answer. So realloc is a special built-in function that allows us to do this whole allocate some new memory, loop over everything, copy it over, and then free the old thing. It does all of that for us. If we had our old plain seats variable, we could just reuse it and tell it reallocate the memory. In general, we've got a question now of by how much should we grow our allocations. So if we grow our allocation, let's say we add room for 1 extra seat. Do you think this is going to be an efficient way to go about allocating memory? Hands on heads for yes, this is efficient enough. Hands in the air for no. So it seems we have a fairly unanimous no going on here. Well, you're right. Pursuant to Dougal's suggestion before, if what we need to do when we allocate new memory is this whole process of copying everything over, then that's going to be pretty inefficient, particularly if we can't get to the state where the new block of memory that we add is just after the old one. In fact, our fancy option 2 is really just option 1 in disguise. The operating system has to do something very, very similar to what you're doing manually here when we do option 2. Now, the details of how the operating system manages memory and whether we can get our ideal situation where you can always just add a little bit at the end is going to depend on what's known as the heap allocator of the operating system. There is a small program inside the operating system that actually manages the memory and decides which blocks of memory you get and which blocks of memory you don't get. If the heap allocator is designed the way it is in common systems, we're not really going to be able to get that very efficient just plugging onto the end. And so every time we ask for a new allocation, even if it's only of 1, the computer has to do all this work of copying all the items over into the new location. And so it probably is a pretty bad idea to grow our allocations by 1 each time. Instead, it might be a better idea to waste some extra memory, allocate more than we actually need to use, but save the effort of copying everything over, because if we needed to add something once, chances are we'll need to add something twice, we'll need to add something 3 times, and doing a copy each time is just not worth it. So take a guess, maybe double the size of your memory allocation. You might waste a little there, but you'll also save yourself likely a lot of time. Now, is this doubling strategy what's going to happen to the space in our computer's memory if every time we just need a little bit, we ask for a lot? What's going to happen if we don't just malloc this for, say, our seats, but we have to use malloc and grow the number of planes we have, and we grow the number of airports we're talking about, and we grow the number of security personnel at the airport? What might happen to our computer's memory? Okay, so the situation was that we have started reserving a whole lot of memory for a whole lot of different things all over our computer's memory. So what happens now if I want to malloc something new? So I've malloced a whole bunch of things already and I want to malloc something new.
Okay. I'm not entirely sure.
Is it easy for our computer to find, like say I ask for 50 slots of memory, is it going to be easy for the computer to find those 50 slots of memory?
I'm assuming no.
Yeah, it might end up being a little bit difficult. And if you think about the organization of the stuff that we've put in already, I'll ask for a block of 300, a block of 800, a block of 1900. Why do you think that might be challenging?
I don't know.
So think about it if the computer's memory is a large puzzle and you have pieces of different sizes. Does it get easier or harder to fit in another piece? Not a puzzle piece. Let's say a board with just an empty board and you have different size pieces of wood and you have to fit all the pieces of wood on the board.
It's going to be more difficult.
It's going to be more difficult to make the new piece fit if you've already taken up a lot of the possible slots where it could have fit before. And so this is essentially what happens to our computer's memory when we start allocating lots of things, and it might be your program's allocated some stuff and other programs have allocated some stuff. We get memory fragmentation. That is, the free bits of memory are not all together in a computer's memory. Thank you very much. Sorry, your name one more time?
Jeff.
Jeff. Okay. Thanks very much, Jeff. And so we actually do have a trade-off to make, just like with many of the other things that happened where we would say trading off on space or time. Here we have a trade-off on allocating more memory against the ease with which our computer can actually find these blocks of memory. And this ultimately is the answer to our question from before of why is it so hard to just add a single +1 to the end? Well, it's because our memory is fragmented, and what our computer's trying to do is to minimize the amount of free space between things so that in the end we have the largest amount of free blocks together. So if you imagine you have a long row and you can put down pieces of wood next to each other on the row, if you want to make it the easiest to put a new block down, you should smush all the other blocks together, leaving as little free space between them so that you have all the free space at the end to put your new block down. And this is why we have so many challenges if you're building an operating system for managing the memory, and why realloc ends up being expensive. We have one or two more traps with our pointers, our malloc, and our plain seat, and our structs to go through. So this is a bit of an easier question. What is the value of plain seats after this code? And you don't have to give me the exact value, you just shout out like, what is plain seats going to contain after? If malloc has worked. Yeah, it's going to contain the address, some address of memory that's been allocated to us. Now, a slightly trickier question with a similar answer. What is the value of plain seats after this code? And Boxiang, you can do this one again for us, because you so graciously answered the last one. So the last time, the answer was the memory address that we got for plain seats. What is it now after we run free?
No address?
Why might it still be the same address?
Oh, because we haven't, I guess, overwritten the address.
Yeah, we haven't overwritten the address. The address still exists in the computer's memory. All we've done is we've told the operating system that we don't want that memory to belong to us anymore. So the memory address still exists, it's just no longer allocated to us. And what happens if we try and access memory that's not allocated to us? Segfold, who said that? Thank you. It's a trap. The pointer still contains the address even after we've freed it. You get a segfault if you try and use it, which is why after you free the memory, you should set the pointer to null to make sure that you don't accidentally reuse it and cause a segfault of your code. Well, we've got a few tips for managing your mallocs. Tip number 1, always check if your malloc succeeded. If your malloc doesn't succeed, you're probably in pretty big trouble for your overall program. It's likely that you've used more memory than the operating system is willing to make available to you. But it's always a good idea to check, because if you think it succeeded and it hasn't, you can end up corrupting the memory of your program even worse. Don't assume that you know the size of a type. We say a char is 1 byte. But the person who built your particular operating system or built your computer's processor might have decided to make different decisions. So it's always a better idea to use Sizeof. Remember, with integers, this distinction was particularly acute because we have 32-bit systems versus 64-bit systems. Grok is a 32-bit system, whereas your laptop or computer is probably a 64-bit system, which means if you hard code that an int is 4 bytes, you're going to use too little memory on your laptop, or you're going to, if you say it's going to be 8 bytes because you're doing it for your own computer, and then you try and run your program on Grok, that also won't work because on Grok you haven't allocated enough memory for the integers. So always use Sizeof, and that will ensure that the operating system tells your compiler just how much memory a given type takes up. Also, don't forget to free the memory you allocated and afterwards to set the pointer to null. We don't want memory leaks. We don't want to be like Google Chrome used to be, at least. And so for every malloc, there should be a free. The return type of malloc, and we haven't talked about these yet, is void star. That's not a very useful type for us at this point because void is a pretty empty type, and we actually want to be using the memory for other types of more meaningful objects like ints and structs and doubles and characters, etc., etc. So it's always a good idea to add a cast to the front of malloc just to keep in your mind what type the memory is going to be used for, and also to let the compiler know. Otherwise, it might give you some warnings. You can get away without doing this, but I wouldn't recommend it, and it's against our style guide. We now have 3 programs to demonstrate what we've learned today, are different little bits about Malloc, Realloc, and Sizeof, and then we'll move on to a data structure if we've still got a few minutes at the end. This is a simple program that prints the size of various different types on my particular laptop on which it's running. You'll notice that I've got these ugly blue bars. The compiler is adding a bit of a complaint next to these lines because it's complaining that LU in format string requires unsigned long, but the argument type is size t, aka unsigned long. So the compiler is complaining that I haven't used the special format specifier to print the type that sizeof returns, because the return type of sizeof is also dependent on what computer you're using. So here, I am going to give full credit to Alistair Moffat for this particular poor example of programming practice.
Change all the L's to Z.
Yeah, I will do that.
ZU.
Yeah, ZU, oops, there we go. And this is the correct format specifier for sizeof. And then we have one more correction to make.
Oh. Save it. Yeah.
It's fine, he made funny comments about my hair today, so this is revenge.
That's pretty harsh.
Where are we? Lecture 8.2. Okay, let's give it a run. And you can see the size of all the basic types on my particular computer. So as expected, a char is 1. On this machine, actually, an int is 4 and a float is 4. I'm not sure what's going on there.
That's usual.
That's usual?
Okay. Because float is double precision float.
Yeah, but I was thinking that I might get...
Long is also 4.
Long is also 4? What's
Yeah.
happening on my poor computer? No, it's not. Liam is wrong. Long
I am.
is 8.
Hell?
Because it can contain, it has twice as many bits as an int on this computer, and so gives us the full 64 bits. But
What is long?
do we want to find out what long is?
Yeah.
Liam, you're being very disruptive today.
Sorry.
We should keep him sick.
It's also 8. Bruh.
Also 8. So our longs aren't really any bigger than longs in terms of the memory storage allocated to them. Okay, and then we have the size of, if we have A was an array of doubles, the size of A was 80. It's correctly reporting the size of all the storage used for the array together. Okay, the size of a pointer to the array on a 64-bit machine needs room for all 64 bits of the address, so that is 8 bytes. The size of P, which is a character pointer, also 8 bytes. But the size of star P, which is the first element of P, is a character, and a character on my machine is of size 1. Our program seems to be working, all good. Okay, next up, we have our basic Malloc program. There we go. We're going to allocate an array of pointers. Here we have a type that allows us to contain an array of character pointers. We're going to print out that we're about to do that. We will allocate using malloc n bytes, where n bytes is 10. And we're going to do this for each index I in our array of character pointers. After this, each of the elements in our array P should have a pointer that points to another another allocation of memory that has room for 10 more characters. So inside P, our array P, inside P are no characters. Inside P are pointers. But each of those pointers, if we follow them along, point to characters. And the way this would look like is P0 would be equal to some address, and then if we follow that along, then we'll have room for 10 characters, etc., etc. I'm not going to type out all 10 characters. If malloc succeeds, if malloc is equal to null, print failed. If it's not equal to null, print succeeded. and then each time multiply n bytes by 100. So keep trying to allocate more and more and more and more memory. And then at the end, we go back, free them all, free each the memory pointed to by each pointer, and also set each pointer to null. The reason why we have this loop and we're looping over is because each of the elements in this array P are themselves a pointer, and each pointer has its own memory allocation. So we've got this kind of two-dimensional structure going on. And so for each of those pointers, we need to free up the memory pointed to by them, and then we also need to set each of those pointers to null so we know not to use them. Let's give it a run. We start with allocating 10 bytes to the first character array, 1,000 bytes to the second, 10,000, etc., etc. Should we do an experiment and see what happens if I make that number even larger? People want to see that? Yeah, okay, so let's make that much bigger.
Don't try this at home.
So we were able to, I'm not even sure how many zeros that is. It's a lot of zeros. I'm guessing when I try and allocate anything more than like 100 megabytes, it's failing.
So it's 10 bytes, 100 kilobytes, 100 megabytes, 100 gigabytes succeeded. And
Yeah,
100
well,
terabytes failed.
one funny thing that's going on here is even though the operating system is saying that we're being successful to allocate 100 gigabytes of memory, how much RAM do you think this computer actually has? Take a guess.
16 max.
I wish I had the 64-bit MacBook Pro. Let me tell you that story, probably for the last lecture.
Salt. So much.
Yeah, I'm very salty. I ordered that MacBook last October. But the computer's actually lying to us. It's letting us allocate 100 gigabytes of memory because the operating system is guessing that we won't actually use the 100 gigabytes, but at least in theory has the capacity to talk about 100 gigabytes of memory. So it lets us do that, but if you actually start filling it up, sooner or later you will overwhelm your computer's memory. You'll run into something called swap, which you can Google if you like, and after that our program is definitely done for. However, eventually the computer gets wise and says, no, you're just trying to do something absolutely ridiculous. I'm putting my foot down here, this memory allocation is failing. One of the reasons it might do that is if you actually run out of enough bits in your addresses to even talk about memory that large. So remember, we discussed last lecture, 32 bits of pointer give us room to address 4 gigabytes of memory on the computer. With 64 bits to represent memory addresses, you get a much higher value. I think, Liam, do you remember off the top of your head how much it is?
64 bits.
Yeah, how much memory you can address with 64 bits?
2 to the 64.
Yeah, I don't remember what that is in terabytes.
It's like 2 quadrillion.
Anyway, eventually you'll run out of bits to address your memory, and the computer will just refuse to allocate you anything. Liam will look that up for us. It's so nice having a tutor in the classroom, isn't it? And we have our final program for today. Oh, Wida has an answer?
Oh, you said 18 exabytes.
80 exabytes of memory. 18 exabytes of memory is the amount that we could address with 64 bits. I can't think of a computer I've seen recently with 18 exabytes of memory, but if you have one spare to use for the front of next lecture, I would gladly welcome it. Except all donations of giant supercomputers would probably take up rooms and rooms and rooms and rooms. Okay, here is our realloc function. And what we're going to do in this one, we're returning to our getWord program before. We're going to get a whole bunch of words, put them in some allocated memory. We'll call this memory all words, and as before, we're going to try and count the number of distinct words. Now, our limitation before was twofold. So the first is, if we remember we saw, I think it was last lecture or the lecture before, our stack size was limited. When I started running off the Moby Dick program and ran the string sort on that, it originally crashed because the stack only allowed me to fill 8 megabytes of data. Then I overrode that and gave myself 65 megabytes, but at that point the operating system stops you and says, nah, you're not putting more than 65 megabytes on the stack, that's too much. And so using Malloc, we can get around that limitation and use even more memory and address even more memory. Use even more memory. We can address even more memory anyway. And so we're going to put all our words in our allocated memory, but we're only going to start off with a limited amount because we're guessing that most people using our program are only going to want to run this program on a small collection of words. So maybe room for 100 is enough. Then we so we've allocated the memory and then we go into our loop. Every time we add a new word into our collection, we first check if our word is one that we've seen before. We want to collect distinct words, so if it's not a word that we've seen before, we're going to move on and add it to our list. If there is a new word, we now have to check, have we allocated enough memory to fit this new word in? Remember, we only have room for 100 initially, so this is only 100 distinct words, and I'm pretty sure there are more than 100 distinct words in Moby Dick, otherwise it might be a pretty boring book. Okay, so we check, is there space? We have a variable that keeps track of the current amount of memory we've allocated, and we're going to see, have we just added the last word that we can fit in? If we have just added the last word that we can fit in, double the variable that says how much our size is, but it's not until we actually run the next line that that becomes true. Now what we do, we reallocate, yes, there was my syntax mistake from before. Realloc takes 2 arguments. The first argument is a pointer to the old chunk of memory that you want to increase in size, and the next argument is how much you want the new amount of memory to be. The mistake in the slide was I'd only given it 1 argument. I'd given it the amount of memory I want, but you need to also tell it where that memory is. And that was something I had forgotten to do, and we'll correct for next time. So we have our common realloc mistake. All worlds nulled but not freed upon failure. Is that an actual error in this case? Oh, we'll have to look at the code later and see if the compiler is just complaining for no reason. Anyway, so we allocate now the new amount of size. The new amount of size, we've just doubled the previous size and multiply that by the size of star all words. Now what I'm doing here, I'm dereferencing all words to get the size of that, the underlying type. So all words is an array. I want to find out how large one item is in the array, and then the current size is going to be the size of one of the items multiplied by the total amount of space I want. And then we run exit if null, which is just going to be a function that quickly checks for error so I don't pollute the code here. At this point, we know that there's definitely space, and so we are going to we're going to allocate room for that word in our array. So firstly, we need to have enough room in our array for pointers to all the words. So we have room for 100 pointers to words, and then at each pointer needs to actually have space for the word itself. Once we've allocated the memory for that word in particular, we then copy the word into that pointer, and we increment our count of how many distinct words we've seen. And the rest is boilerplate code that we have seen before. Let's give this one a run. Oh, it's expecting input, and I didn't give it any. We'll feed in Moby Alpha, the same text file that I showed you yesterday with Call Me Ishmael and the full text of Moby Dick. And we have 19,472 words. And some of those words look like I accidentally removed spaces when I constructed this text file. So death gasp would be a wonderful single word. If we have any essays submitted later in semester, I highly encourage you to use that. Unfortunately, I don't think we have any essays on the calendar. But you can see our program works. It handled much more than 100 words, even though there was only 100 words initially, room for 100 words. One thing I want to make clear again, because this is a little confusing, our all words variable is a pointer to a pointer. This means it's kind of like an array that contains pointers, and each pointer references a word. Because remember, a word is a pointer itself. It's a character string, and so you need to store that in a pointer. So if we want a set of words, we use a pointer to a pointer. The first pointer gives us the set of all the pointers, and if you dereference that, each of those pointers points to the character string itself. This program might be one of the first times that you're encountering these pointers to pointers, and so I encourage you to step through this one a little carefully. We have a few more minutes, and that'll leave us with just enough time to set up our problem, but I'm not sure it'll actually allow us enough time to really dig into it. So we might have to leave that for a very, very exciting first lecture next week. And Liam B., who is also sitting in the front row, will hopefully be around to give us a bit of a demonstration. Let's do a really fancy transition this time. There we go, fancy transition. We're having a good day. This is a view that we've seen before of our computer's memory. We have the stack, which is all our normally declared variables, and our heap, which is where all the memory that we allocate using malloc goes. Remember, the stack grows down. Every time you add a new variable to the stack gets a little larger, and the boundary of where we'd allocate the next item moves down. The heap is the opposite. Every time you allocate memory using malloc, if you exceed the boundaries of the heap is going to grow larger. We talked a little bit about this heap allocator, so we know that it's not going to be growing, they're not all going to be consecutive within the heap, so you might have some free spaces here and there. But if you exceed the amount of room available in the heap at the moment, that boundary is going to grow a little higher. And eventually, if the heap grows higher and the stack grows lower, they might eventually meet, and we would get a segfault. Whoever said that. The final question we have for today starts taking us into our new problem for next week. And we will probably recap these slides in the next lecture. What is the fairest way to distribute Hamilton tickets? This is an open question for the crowd. You can put your hand up if you have a good idea.
Give them all to Chanel.
That would be lovely, but I've fortunately already seen Hamilton, so we'll gladly give my next ticket to one of you two. So what's a fair way of distributing Hamilton tickets? 200 people who want Hamilton tickets. Highest bidder wins, okay, that's one. Highest whams. I like that idea. Although I can't promise that the top student in the class will get Hamilton tickets or the lowest student, I just don't have enough. Okay, what do you think? What's the best way to distribute Hamilton tickets?
Make it lottery price. Then just randomly pay.
Ranked by price? What about first come, first served? Do you think that's a reasonable mechanism?
Reasonable.
Yeah, so what does it look like when you have a really popular event and the rule is first come, first served? What happens? Let's say we're ignoring websites. You have to buy them in the real world. What do you get?
Everybody.
Okay, we'll pass it over here. And I'm so sorry, but your name escapes me today. Adam.
Everyone starts waiting a lot before the event actually starts.
And they wait in a
queue.
In a very long queue. And over time, what happens to the queue?
It gets too long.
It gets longer and longer and longer. People keep getting added to the front. And then when the ticket window opens, what happens to the front of the queue?
They get a ticket.
Someone gets a ticket, and then what happens to them? Do they stay in the queue?
They leave.
They leave the queue. Okay, so this is going to be the setup for our next data structure. We have our first come, first. Keep holding it for a minute. We might have one more question for you in a minute. We've got our first come, first serve setup, and we need a data structure to represent what's going on here. So can you give me one idea of how you might represent the queue?
Array.
An array. So what would we do every time a new person joins the queue? What would we do in our array?
We add to the end of the array.
So to the end of the array, we would go all the way to the end and we'd add the details for the new person to add them to the queue. What about when the ticket window opens? What do we do then? And someone gets a ticket.
We remove the first one.
So we could remove the first element of the array, but now if someone joins the other end of the queue, we've still got an empty spot at the front, don't we? Because we just removed the first thing in the queue.
Yeah.
So what's going to happen to the amount of memory that we're using as the line gets larger?
More and more.
More and more memory, and even if people leave the queue, we're going to have removed them from the front in the array, but we still are going to be adding more and more to the end because we aren't using those positions in the array anymore. So what's one solution to this?
Like every element can shift forward to take.
Yeah,
the
so
next
if someone leaves the queue, whether it's at the front because they've gotten a ticket or in the middle, we shift everyone behind them up one. What might be a problem with doing this if we're on a computer? Is this a... Go ahead.
Too much like calculation, like too many
This
steps.
seems like a lot of work. We probably don't want to be moving everyone along in our memory representation every time that someone leaves the queue. While this might make sense in a physical queue because people moving along, everyone just shuffles their little bit. When if you can imagine if you were the, you know how sometimes there are those security guards that stand outside the front of the queues? If every time someone left the queue, the security guard had to go and pick up everyone and put them one space along, it's probably not going to be a very efficient use of anyone's time, although the security guard might have a very interesting morning. So this doesn't seem like an ideal way of representing it for the computer. Option 1, nah, worked okay. Option 2, let's build a new data structure, something to act much more efficiently, that is efficient for both when we add something and when we take something away, and in particular from the start and the end. Yep, I know. And that is going to be where we will leave it for today. Next week, we will learn about this data structure, the linked list, and we will have an exciting live demo with props. I hope you're looking forward to it. I'll see you next week for our last week together before I go away.